All right, guys. So today we're going to be talking about something called kinematics. And it's typically the first topic that you'll encounter in an introductory physics course. At its most fundamental definition, um, it is the study of motion without forces. And so typically we'll be talking about particles. And a particle, it's not like a dust particle or something. I mean, it can be, but really in physics, it can be a baseball, it can be a train, a semi truck. In this case, we're just going to be talking about objects in motion. Now, in our study of kinematics, there are going to be some governing equations that will form the mathematical framework which we will employ to solve these problems. These three equations are known as the constant acceleration equations. As the name implies, they can only be used to analyze the motion of objects whose acceleration is constant throughout the time interval that you choose to analyze them. While I'm writing the rest of this down, think about what non-constant acceleration might mean and what it might indicate for a system. In the meantime, we will just be considered with constant acceleration, however. These are our three governing equations that will construct our framework. A couple more relationships to note involving calculus. We're going to say that the velocity of a particle at time t is going to be equal to the rate of change of the position of that particle at that same time. Similarly, the acceleration of a particle is going to equal the derivative of the velocity with respect to time. It's always helpful to draw a schematic, and so I'm going to do that over here. We'll use a pickup truck in our example. There's a couple things I need to note here. I want to talk about the motion of this particle, or the motion of the vehicle. So I need to define which way is up and which way is down, or in this case, which way is forward and which way is back. The position of the particle is given by the symbol x. So now that we have defined our coordinate system, we can begin talking about different states that this particle can be in. The first one we're going to talk about is at rest. This indicates that the position of the object is not changing. This means that the change in the object's position is equal to 0. And we just defined that the change in an object's position is its velocity. At rest indicates that velocity equals 0. Our next case is constant velocity. This indicates that there is no acceleration, right? We can draw the velocity vector on the schematic like so. And in the time interval that we choose, this velocity remains the same. Therefore, acceleration equals 0 because velocity is a constant. Okay. Now, we can look at the case where acceleration is not 0. And one thing I should point out is that we did mention earlier acceleration is the change in velocity with respect to time. And if the velocity is constant, well, the derivative of a constant is just 0. And therefore, acceleration is 0. Further reinforcing what I just said about motion of constant velocity. Now, let's say the vehicle is approaching a stop sign. This vehicle has to slow down. And so therefore, it has to accelerate in a negative way. Now, we can leave the vector and the symbol like this, or we can choose to negate the symbol and simultaneously flip the direction of the arrow that it is associated with. I prefer this way. At this point, we are assuming that there is a constant acceleration acting on the vehicle. It starts with some initial velocity and it slows down. And so we can kind of see that in the case with the constant velocity, we're going to have this graph, and we'll call this the position versus time graph. We can also do velocity versus time. We can do acceleration versus time. There are many different variations of these diagrams, and you pick the one that is most useful to you. However, with a equals 0 and a constant velocity, you notice that your position is changing at the same rate. In other words, the slope of this line does not change from the time that you started measuring to the final time of your study. Under the negative acceleration, or the deceleration, as some will call it, your position is changing very fast before you slow down, so the slope or your velocity is super high. But then that slope falls off as you hit the brakes and come to rest at this final position that happens at the final time. Okay? Similarly, if the vehicle is accelerating and not decelerating, so let's say it's starting from rest at some position 0, and it begins to accelerate through some time, the position will be changing very slowly as the velocity is a small number at the beginning, but then as you increase your velocity, the slope of your position increases with time. So I hope this makes sense. This is a good framework for it. We're going to do a small problem that's pretty fundamental, and I think that it'll kind of solidify the concept a little bit, but we'll say that a car is started from rest, and we're going to say that it accelerates at a rate of what we'll say it accelerates uniformly. So this is a clue. Also, starting from rest is a clue. And then we'll give our knowns here. So acceleration is always in units of length, or length per time squared. And we'll just say for 5 seconds. So what can we get out of this? We can say determine the final velocity at the 5 second mark, right? Final velocity refers to the velocity value at the final time that is listed in the problem statement, which is 5 seconds. And determine how far it went, how far it traveled, which is really just how far it is away from the point that you assigned to be position equals 0 or x equals 0. All right, so let's just look at this. Pause the video for a second and see if you can solve this using our equations here. And I'll just give you guys a moment to do that while I begin solving it now. Okay, so one thing to note, we weren't given a starting position, right? So what's x naught? Well, it's convenient that we're allowed to choose our own custom inertial reference frame. So I could really choose anything I want, but to simplify this calculation, I'm going to choose that we're starting at the origin. We're starting at x naught equals 0. Okay, starting from rest, I kind of already gave it away here, but v naught is 0, so we can write that here as well. And that means all that I'm left with is that the final position after the 5 seconds, given these acceleration conditions, is just 1/2 times 3 times 5 squared, and that's going to be in meters, and that value is 37.5. So the vehicle traveled 37.5 meters, and the final velocity is 15 meters per second. So I hope this helps. If you enjoyed the video, please like and subscribe it. Subscribe to my channel. There will be many more like it. And if there's anything that you would like me to do or cover, I would be happy to oblige. Just mention it in the comments. Hit the bell notification if you would like to be notified next time I release one of these videos. Likely will be very soon, given that I have a lot of time over the summer and I only work a full-time job and do not attend classes. So please feel free to reach out, send me an email, whatever you like. With that said, have a wonderful day, and I'll see you in the next video.